list of the formula, instead of the pressure explicit derivatives, you are given the formula in terms of two coefficients which are related to the derivatives of pressure with respect to volume and temperature. This is the coefficient of thermal expansion. It is how the volume, specific volume changes with temperature, a constant pressure, and that is how it is defined. And then the other quantity is the isothermal compressibility. This is coefficient of thermal expansion. This is isothermal compressibility, defined as minus 1 over V dV by dV at T, constant temperature. That's why it's called the isothermal compressibility. Constant temperature. Compressibility refers to how the density of the specific volume changes with pressure when you compress fluid, right? So that is what this coefficient gives. And you can see that there is a negative sign for the definition of isothermal compressibility, so as to make the coefficient positive, because we know that dV by dV is less than V. So dV by dV is just the inverse of that, it's also less than V. So this would ensure that the isothermal compressibility is always positive for a substance. So, I mean, these coefficients, if you see maybe older tables or maybe Sandler, you make a calculation of these properties for various substances. So, possibly in some of the older books, it was practice to represent everything in terms of these coefficients, but later on it's now more common to find an equation of state. There is a lot of work done on equations of state to find the accurate equations of state. So we would rather what we wrote down in the class were all the coefficients expressed in terms of the equations of state, the explicit pressure, explicit derivative. Whereas these are in terms of it, but nevertheless you should be able to derive all the formulas that we at least show that these are equivalent to the formula that we have already derived in the class, and other formulas that we have left out involving coefficients for A and G. Those I believe you could derive them by yourself in whatever form you want. But anyway, answer in what is one form is given. Are there any questions on this new coefficients? Some books define it as alpha, the coefficient of thermal expansion, but we have chosen beta. That seems to be more common in thermodynamics text. So you should be careful when you look at particular textbook. In terms of textbook, also some complain they haven't received the is there anyone who hasn't received the syllabus sheet? Doesn't have it has a listing of textbooks and so on. So anyone who wants this sheet, I distributed maybe last week. Anyway, if you're in need of it, you can collect it. But there textbooks are given, and if you look at the, I give you might have to refer to many of the certain topics are covered better in certain textbooks. If you want to, the single component, we can broadly divide the whole course. First, if you take non-reacting, no reactions are considered. Right? Then we can look at two cases. One is C equal to 1. It is component. Number of components is 1. Right? And number of components is greater than 1. Of course, you consider C greater than or equal, you consider C greater than 1, automatically the result for C equal to 1 would follow from that. Right? So we can generally consider C greater than or equal to 1, arbitrary C, and then deduce the result for number of components equal to 1, but that is not what is followed normally, because it just becomes very confusing. Better to learn some of these techniques for the single component, right? And then move to binary and ternary and other mixtures. So in this, we can further divide it into pi equal to 1 and pi greater than 1. That is pi denotes the number of phases. So pi equal to 1 refers to homogeneous. This is what we are doing now. Right? Pi greater than 1 is more than one phase. What are the complications that arise? Similarly, we can consider, here also first we consider homogeneous state. This is progressive increase in complexity, and that is much better than deriving everything from C, arbitrary C and arbitrary phi, and then specializing it. And that is not the way it is normally done, and maybe for a good reason. So maybe in an advanced book to summarize everything, you can just write down all the necessary equations for the most general case, but not in this course. Then other is reacting mixtures. Automatically, the reaction itself means the transformation, chemical transformation. No question of C equal to 1. Even an isomeric transformation, there is a transformation from one type of isomer to another, that is to be regarded as a new component. The chemical formula may not change. Right? So automatically we are forced to consider only C greater than 1. There is no question of C equal to 1 in reaction. Actually, one substance is converted to another one or more substances. So you have to consider mixtures like at the outset. Here again we can consider pi equal to 1 as a homogeneous reaction mixture and pi greater than 1. So we are right now here. We soon take up the this, then we will move to this, and then to this, and finally to this reaction. The most complicated probability that we cover towards the end of the course is combined phase and reaction equilibrium. That is what there is. In terms of textbooks, I would say the first textbook, YVC Rao, is quite good for C equal to 1. Single components, it is very crisp and clear, compact as compared to, for instance, the other well-known textbook, Sandler, which is very laborious and very verbose, a lot of more details than what we require. Right? So C greater than 1, I would say probably Sandler is a more reliable book. In terms of definitions and all, it's more precise. Right? So I would say if you want one textbook, I would probably prefer Sandler. If you want to buy, for instance, a textbook, I would probably recommend Sandler. YVC Rao is also quite okay. In terms of other books, Talent is more on fundamentals. We refer to, whenever I find that some topics are covered better in any of these textbooks, I will indicate what sections you have to go and read. So that you don't have to buy all the books, but you might then refer to them in the library or whatever. Talent is mostly followed by physicists. It's very good in certain fundamental aspects of but it's not, it doesn't require, it doesn't discuss applications in detail. So you will find big discussion on how to compute vapor liquid equilibrium and all that. But for basic fundamentals, it's quite well-known book. So these are some of the books. Structural model is again somewhat advanced book. Certain topics maybe we might require. I'll refer to it whenever. These are all, some of these are, but probably these are the important, like I would call textbooks. Forestry is a more recent one, but I haven't really looked at it in detail. You might want to consider that as additional reference, right? So the Smith and Van Ness, I would say it's a very old book, widely followed in earlier. This is, I find, very good for problems. This is a very good, interesting problem, especially in later vapor liquid equilibrium, reaction equilibrium, and so on. So all these books have their pluses and minuses. Are there any questions on this? The references and so on. Okay, if not, what we will do is we take up 2 or 3 of these coefficients which we haven't introduced but which are dependent on or which can be derived from has a maximum in density at 1 atmosphere at 4 degrees centigrade. And so we're going to plot the E versus T. Let's say I put T here and B here. There is a specific volume. So specific volume is inversely proportional to the density. So what it has a maximum density at 4 degrees, then the specific volume would have a minimum at 4 degrees. Right? So at 4 degrees centigrade, then I have minimum B at 4 degrees. So now we can ask, what is the nature of the equation of state? This is a section of the equation of state. It's an isobar. That's very important. Because P equal to P of VE would be a surface. P expresses the function of volume and temperature. Very difficult to draw that surface. It's you have to plot it on a 3-dimensional plane. But when I take a section at a constant pressure or constant temperature, whatever you want. But I am taking here a constant pressure section. And if P is fixed, equal to P naught. This is an isobar. Right? So now, consider only this. An isobar, right, would have this form. V of VE is P naught. So clearly, this defines a curve in the VE plane. So let f of x by 2 is 0. You bring the P naught to the left hand side and make it as P bar of T minus P naught equal to 0. And if something like that, that defines a curve on the VE plane. Now we've already plotted what the curve looks like. If you recall, dV by dt at constant pressure is a derivative of V expressed the function of T and P with respect to temperature. When pressure is kept fixed, is given by minus dV by dt. So how is this quantity related to, can I calculate that quantity from the graph? It's the slope of the curve, right? Because even though it's a function of two variables, here I take the derivative and then I'm fixing the pressure at P naught, right? So obviously this becomes like here, since I fix the pressure P naught is let's say 1 atmosphere. Whatever I take, I write it as dV by dt. Because I'm looking at a curve, say dF by dx, f prime of x, right? So clearly, what you have to recognize is that is the same as this quantity. It is written in terms of partial derivative. So what we infer from this is that clearly what happens at 4 degrees centigrade to this coefficient. dV by dt. What is its value at 0? 0. 0 equal to minus. What can you say about the right hand side? That's also 0. Now about the individual terms, can you say anything about dP by dt?
0.
What can you say about the value of dP by dt at T equal to 4 degrees centigrade? It is 0, but not because the pressure is constant. We have to distinguish between that P naught here and this derivative, which is valid even along because the isobar is a curve on the surface. So I can talk about the derivative dt, which is a common confusion. What you raised is an important question because people ask, if you consider an isobar, like everything is 0, then this is also 0. So we have 0 by 0. That is observed. That is not what it means. So you have to distinguish between these derivatives. Right? This is the by dt is valid because the isobar is also part of the surface. It's valid on an isobar as well as on any other curve or any other point on the surface. You have to regard this when you're looking at this derivative. You have to regard this as a point on the surface P equal to P of dt, but evaluated at P naught equal to 1 atmosphere, T equal to 4 degrees centigrade, and B equal to whatever. Right? So what can you say about this? This we know, we have assumed all along that this has to be less than 0. Otherwise we cannot make any sense. That this formulation depends on the fact that this is not 0. This is clearly less than 0. And so dP by dt is also equal to 0 at 4 degrees centigrade. So what can you say about the value of dP by dt? To the right of 4 degrees on this section of the curve, what can you say about the derivative dP by dt? Is it greater than 0 or less than 0? How do you arrive at that? dP by dt is negative, so the negative will cancel with this. So the sign of dP by dt is the same as the sign of the slope of this curve. Clearly, geometrically, you can clearly see that the slope is going to be positive. So this would be, which I said is a typical. So the anomalous behavior is not for temperature greater than 4 degrees, but actually for temperature less than 4 degrees. That is not quite typical, and here in fact is less than 0 to the left of 4 degrees. Yes? Huh? Yeah, what is it that you want?
You said that
Huh? Yeah. So what I am saying is that let's write dV by dt on the curve is equal to minus now we have already said that this has to be less than 0 for all substances that is taken. Right? So this is less than 0, so this will cancel with this negative sign, becomes positive. So that doesn't make dP by dt positive. It means that the sign of dV by dt is equal to the sign of dV by dt. Right? That is clear. So we get dP by dt is greater than 0 to the right of 4 degrees and less than 0 to the left of 4. So the equation of state for water around 4 degrees should reflect these properties. Otherwise it cannot describe this very complicated property. It doesn't happen for most substances. Right? But what can you say about Cp minus Cv? We have expressions for Cp minus Cv. What can you say about Cp minus Cv at 4 degrees? At 4 degrees. Less than 0. At 4 degrees centigrade. At 4 degrees. You think the answer is too trivial to respond, or you don't know the answer and surprise? You have the formula. It is 0. What is Cp minus Cv? I don't exactly remember this, but if I remember right, dP by dt squared by clearly it is 0 for dP by dt is equal to C. Cp is equal to Cv. But what can you say about Cp minus Cv for d greater than 4 degrees centigrade? It is greater than 0 or less than 0? Greater than 0. What can you say about Cp minus Cv for d less than 4 degrees? greater than 0 because Cp minus Cv, the difference, this is again, this negative will cancel with this, but however d is anyway positive, but the difference effectively depends on dP by dt squared. Cp is always greater than Cv except when dP by dt vanishes. That happens. It's probably an unusual instance where Cp and Cv, you should remember, the universe, one value for any substance depends in general on both pressure and temperature. Right? So for water at T degree centigrade, 4 degrees centigrade and 1 atmosphere, Cp is equal to Cv. So that is what is clear. Other places Cp is simply greater than Cv always. It can never be less than Cv. So any questions on this? Next coefficient we'll take up is, this is covered in most textbooks, especially in YVC Rao, and briefly discussed. This is also a lot of it. So I'm just picking one or two important historical, three important coefficients. Right? The next one I will look at is the speed of propagation of sound in a medium. The thermodynamics is quite significant. It relates to the work of Laplace, who assumed the propagation of sound is an adiabatic process, right? And so this leads to a formula for V acoustic, it's often referred to as acoustic speed. Actually, right? V is given by square root of along an adiabatic process, right? Pressure can be expressed as a function of density alone. This is now the mass density. So very famous formula from hydrodynamics and so on is that speed of propagation of sound is actually given by this, right? This formula was even adapted by Newton and so on. There's a lot of historical background. This is the mass density. How do we calculate this? Right? We calculate this because we see that in an adiabatic, of course, reversible, which is assumed here, simplicity assumed by Laplace. And so, in adiabatic reversible process, we know that the entropy doesn't change. So, it becomes an isentropic process. You might have all seen that the way to derive Pp for gamma is a constant for an ideal gas is by assuming this. The entropy is a constant. So the entropy is a constant, so this derivative what we need actually can be written as dP by d rho at constant entropy, because the constant entropy is equivalent to the reversible adiabatic process. So now the derivative, this is a mass density, so first we will look at dP by dV at S. We don't know anything about the coefficient. The formula for coefficient can be easily derived. But obviously, what would be the correct starting point? Good starting point would be what? Is what is it commonly expressed in terms of? So we want all these quantities expressed in terms of the equation of state. Right? So obviously, it would be V equal to Vt. Now I say what should I do to express P in terms of B and S. Right? So clearly, what is the answer? That means I have to express T as a function of S and D. We already have derivatives for S as a function of B and D, so clearly that is not going to be a big issue. So what we say is, I consider this, and from here, using the chain rule, I can get dP by dV at S dV at S. This is already in terms of pressure X, because our objective. You finally get a very compact formula for the acoustic velocity, the speed of propagation of sound. All I have to do is reduce this dP by dV, right? So you can easily see that this is coming from S of dP to E of SP. That one dP by dV, not dT by dS. So dP by dV at S will have a negative sign, right? ds by dV at T by ds by dT at T. You can easily get this from the implicit or inverse function theorem. So now what do we do with this further? What is ds by dV at constant temperature? Because of pressure. Look at the Maxwell's relations. So you should get familiar with this so that you remember some of the important relations to help you. Right? dP by dt at constant volume. What can you say about ds by dt at V? Cv by d, right? So this will be minus T by Cv, Cv by dt at V, and so I get dP by dV at S is equal to but we have already seen this factor T dP by dt, the whole square, comes somewhere. Where does it come? We just wrote that formula down. Which formula? Cp minus Cv, right? So we know that Cp minus Cv is minus T. So I can replace minus T dP by dt whole square by Cp minus Cv times dP by dV at T. That's what I put. So I have now dP by dt will turn out to be a constant factor. I have one minus T dP by dt square is Cp minus Cv. Of course, I have taken out the constant factor. It's not a constant, it's a common factor. Right? So I clearly get this will be 1 plus Cp minus Cv by Cv, which is equal to Cp by Cv times dP by T. The Cp by Cv is a new factor. The gamma, the ratio of specific heats, right? So this is gives a what we now get is dP by dV at S is gamma times. This is an important formula. What we have done, because what we want is any coefficient is possible, wherever possible. We want to express in terms of Cp or Cp or both, and equation of state derivatives, quantities. And so that's what we have done here. Now V and rho, of course, are inversely related. You can easily show that these specific volume is the volume per mole, whereas rho is the mass density. It's the mass per volume. So they have an inverse relation, but one is mass and another is mole. So we can easily show that V equal to m over rho, where m is what? M. What can be m? Molecular weight of the substance, whatever the substance I'm considering, the medium. M is the molecular weight. So the derivative of pressure, for instance, with respect to volume is very easily related to the derivative of pressure with respect to density, because they are just related by a constant factor. So for instance, I can easily show that dP by dP at S, or dP by d rho, I have already got dP by dP, is dP by dP at S. Right? Then V express the function of rho would be simply minus m over rho square. So that's the derivative of, so it's dP by dV, that's dV by d rho. But V is simply a single variable function of rho, there are no other variables. Right? So we get that by just differentiating this with respect to rho. That's what we get. So dV by d rho at T is also dV by dV at T times minus n over rho square. That also doesn't change the relationship between the two derivatives. Each one of them is multiplied by minus m over rho. So this you have to understand, because the velocity has meters per second. So obviously, we need to express everything in mass units. Otherwise, the units will not match. That is why it's common to bring in the mass units larger than the mole here. That is why it is coming. So now what we have is really, this is square root of dP by d rho at S, and now I can write this also square root of gamma times dP by d rho at T. Right? Because I've shown that dP by dV is gamma dP by dV at T. dP by dV at constant S is gamma times dP by dV at T. But if I just substitute this, right, if I substitute for dP by dV at S here, then minus m over rho square is going to cancel out. So I get the same relation. The dP by d rho at S is also equal to gamma at T. You get that you can easily condense yourself, right? So that's what I have here. So the important relevance of this for us would be when the gas is an ideal gas. When the gas is an ideal gas, then we can easily write P equal to RT by P, right? So dP by dV. The constant temperature is minus RT by P squared. What I want is dP by d rho at T, right? And I know that dP by d rho at T then for the ideal gas would be simply minus m over rho square times the minus here, minus RT by T square. M square, and the minus sign would cancel, so we get this formula that dP by d rho at T for the ideal gas, this is for the ideal gas, it will be RT by the molecular weight of the particular substance. We regard as behaving like an ideal gas. This is what Laplace derived all this. Right? So what we get is that the velocity, speed, propagation of sound is simply given by gamma RT by M. So this has great historical significance because Laplace, when he derived it, he wanted the data available on the speed of propagation of sound in air, for instance, and it showed that the speed of propagation was actually proportional to the square root of the temperature. What does that mean? Speed of propagation is proportional to the square. That's what you observe experimentally. What can you say about gamma? Velocity is related to RT by m times gamma square root of. The experimental evidence shows that the speed of propagation of sound in air, which is very well regarded as an ideal gas from a long time back, is under normal conditions of temperature and pressure. Right? If the experimental data is available, then what can you say about the gamma? What can you say about it? Yes. If experimental evidence were not available, then from the equation can you conclude that velocity of propagation is proportional to gamma is a constant. It's a very important thing of conclusion. You know that not necessarily gamma is only an approximation. That's what you know. Both Cp and Cv are essential functions of volume and temperature or pressure and temperature. Ideal gas main property is not that the gamma is a constant, but Cp minus Cv is a constant. That is not accepted. Right? But this seems to suggest that the gamma is a constant for the ideal gas and the concentrated. But today, reasons this result of Laplace was ignored. We don't have the time to discuss that. But definitely, right, I can use a constant value of gamma for air and get this. And if you refer to YVC Rao, maybe I'll give that problem in an assignment next. He discusses an application of this in the propagation and sending and receipt of sound signal, the time it takes and how it is related to the distance. So if we're sending a sound wave from some point and we don't know some obstacle or something is there, let's say, right, in the medium. So when it hits the obstacle and again receive, it travels twice the distance. So from this formula, we can calculate the distance possibly where the obstruction of object is. Right? We will look at how we summarize that in a problem in a statement sheet. Now what I want to discuss is another very important and historically significant coefficient. Very trivial to solve once you have the formula. Joule-Thomson coefficient is very well discussed in challenge. Joule-Thomson effect. Joule-Thomson coefficient is defined as standard notation. It's not to be confused with the chemical potential because I'm putting a subscript Joule-Thomson. It's not a chemical potential associated with Joule-Thomson. The symbol typically given for the Joule-Thomson coefficient. It is defined as E by a constant enthalpy. Derivative of temperature with respect to pressure, constant enthalpy. Where is this significant? Significant in the Joule-Thomson process. When you have a fluid undergoing what is called as a throttling process. Basically a sudden expansion. A sudden expansion. And so expansion means what can you say about the pressure? Pressure will decrease. So it is an expansion process. There is a decrease in pressure. And it's used for cooling derivation of that, we don't get into that, because it will require first law of flow processes, which we have not yet considered. Right? So we have taken given to us, this is a Joule-Thomson quotient, and want to only estimate the coefficient. So dT will give the change in temperature to a change in pressure. This is a constant enthalpy process. This is the coefficient we get. Right? So the pressure is going to decrease. Right? Then the temperature will also, because that is the purpose, the temperature also decreases. Then what will happen to the coefficient dT by dt? It will be positive, greater than 0. So we really want, if I want cooling, I want to have conditions such that the Joule-Thomson quotient is actually greater than 0, because the whole purpose is to reduce the temperature, and we are doing an expansion process, the pressure will decrease. The temperature will also decrease, which the Joule-Thomson quotient is positive. Right now, in terms of how we evaluate this coefficient, what are they evaluate? Can we evaluate them from the formula that we have derived for the enthalpy? Which formula would come in? Which representation I should consider? We should consider E as a function of V and T, E as a function of P and D, and so on. Now, what we need to consider? P and T, very straightforward actually. Right? It is a function of P and T, but this considers T as a function of P and H. That is how you get that derivative. Very easy to see that dT by dt and H is equal to the negative of the original derivative. So I want dH by dt. The inverse function, we give this formula, minus dH by dt by dH by dt. So that's what the inverse function gives. Then it gives the derivative to the new function, it doesn't give the derivative to the old function. The old function for us is equal to dt. We have to now, that the formulas are already given, right? You can easily derive that. We will discuss the consequences of that in the next class and take up the assignment problems on Monday.